So I hope by now you're experts on standard permutations. So this chapter 15.4 is what we're on for this video lesson, is all about permutations involving repetition and then also circular permutations. So there are going to be some special types. So to introduce this idea of a permutation with a repetition, I want to take a look at this simple example here. First one is to write down all the possible arrangements of the word day. So if you thought about that from standard permutation land, you'd have three objects, D, A, Y, and we want to arrange them three at a time. And order is going to be important because we want to look at words here. So we'd expect to find 3 factorial or 6 arrangements. So let's just go ahead and write those down. We have D, A, Y, D, Y, A, Y, D, A, D, Y, and then Y, A, D, and Y, D, A. So there's our 6. Next, in letter B here, let's write down all the possible arrangements of the word dad. Well, we have 3 objects here, D, an A, and a D, and we're taking them 3 at a time. So our initial inclination is that we might have the same 6 arrangements, but let's go ahead and try and write those down. If we actually write the words here, we get dad, of course. We can do add, and we can do DDA. But if we try and write any other ones, we're going to come up with all versions of the same thing. So in this case, we're only going to have 3 different word arrangements that we can make with these 3 letters, DAD. And so the question that might strike you here is, well, what accounts for this difference? And it shouldn't be a surprise that the difference is going to be related to the fact that we have these 2 repeated letters in the word dad, and we had no repeated letters up here in day. And so that's what we're going to talk about next. So that preceding quick example showed us that fewer permutations result when we have some of the objects that we're rearranging being the same. And in dad, the 2 D's were the same. So let's consider this example to see this more clearly. So if let's take a look at Mexico versus Canada. If we're going to rearrange the letters in the word Mexico, well, we would use multiplication principle or permutations. It's going to be 6 letters that we're going to arrange 6 at a time. And in this case, we'll get 6 factorial, which would be 720. There's no repeated letters here, so we don't have anything to worry about, and we'd have 720 different arrangements of the word Mexico. Now for Canada, first there's 6 letters here, but we know there's 3 A's. Let's consider first, let's make these A's distinguishable, meaning that they're not going to be the same letter. So I've indicated that here with these 3 different letters of a red A, a green A, and a blue A. If we were to go ahead and write the ways we could write the word Canada where the A's are in fact different like this, well, we'd get the same thing as Mexico. We'd get our 6 factorial arrangements and we'd be done with the problem. But then when we take a look at, so of those 720 arrangements of Canada, we would see off to the side here, we'd find these 6 particular arrangements embedded in there. And if you looked at these closely, you'd see that all the colored A's are in different spots. But then when we maybe turn the color filter off, you'd recognize all 6 of these arrangements as literally the same word, nakada. And that's what we want to take account of when we permute the word Canada. Well, there's 3 A's in here, 3 different colors. Well, how many arrangements of those A's do we have? Well, that would just be 3p3 or 3 factorial. And so it turns out that's exactly what we're going to divide this by to get rid of the fact that the A's are indistinguishable. We have 3 of them. We could arrange them in 3 different ways, and we're going to go ahead and divide through by that. And so when we do this, you'd get 720 divided by 6 would give you 120 arrangements of the word Canada. And so the fewer number of the arrangements of the word Canada versus Mexico is related to the fact that there's those 3 A's occurring there. To generalize this a bit further, the way we're going to think about this word Canada is that it's going to have, we know it has 6 letters, but then we want to think about types of things within these letters. So we're going to think about the fact that Canada, we're going to say it has one C, one N, one D, and three A's. And so we're going to call these essentially the types of things that we're going to permute. So in this letter, we'd have 6 letters with 4 types of things that we're going to rearrange. And it turns out that the general way to think about this is the number of permutations of the word Canada here would actually be, we're going to have a factorial for each one of these types. So we know about the 3 factorial because the A occurs 3 different ways. But there's also factors for the C, N, and D. They just end up being not important in the final calculation. With the letter C, when there's only one of them, there's one way to rearrange that C. So we'd have a 1 factorial in here. Same thing with the N. There's one way to arrange that N. And then there's one way to arrange that D. Maybe you're asking, well, why am I bringing it up this way? Well, the idea is that we want to be able to generalize for any set of repetitions. So this will motivate the primary formula from this chapter, which is how to do this in the general case. So the formula here then would be, if I have a set of n elements, so in our Canada example, n would have been 6 with k different types. Again, in the Canada example, we have 4 types, the 4 different kinds of letters. And then then the number of distinguishable permutations are, well, the first thing we're going to do is we're going to divide up the n elements into different numbers. So we're going to say n1, n2, n3, down to nk. So we have k different types. And this is just going to be the number of type 1. This will be the number of type 2, etc., down to the bottom where we have the number of type k. So again, in this Canada example, n1 would have been 1, n2 would have been 1, n3 would have been 1 because we had, that was the C, the N, and the D. Then our fourth one, n4, would have been 3. These are always going to add up to n. That's a key thing, is we want to know that the number of all the things has to add up to the entire set of elements. So once we've defined the problem this way, the number of permutations then is just going to be, well, it's going to be our n factorial. So that we're going to start just like we did with Canada. We're going to arrange everything assuming that the repeated letters looked different to us. And then we're just going to divide through by all the sets of repetitions. So we're going to count up how many types of type 1 there are. Well, we're going to divide by n1 factorial. And then we're going to do the same thing for type 2, n2 factorial, n3 factorial, all the way through nk factorial. So don't be intimidated by this formula. Really, the intuition is you just arrange all the letters assuming there's no repeats. That's what's happening on the top here. And then you just divide through to cancel out the fact that you might have repeated letters. And a lot of times these are going to end up being 1 factorial. If you have only one type occurring like we did with the letter C in the word Canada, well, you're just going to have 1 factorial. In practice, you probably wouldn't even write those 1 factorials, but this, in fact, here is going to be the general formula for permutations with repetition. And once you understand how it's derived, it's pretty easy to remember. So now on to a few examples. Here, our first example here is probably the most famous problem of distinguishable permutations, and it's how many ways can we write the word Mississippi? It's a nice example because it has lots of repeated letters. So the way we're going to approach this problem is the first thing we're going to count up all the letters. What's our n in this problem? Well, Mississippi has 11 letters, and if they were all different letters, we could just write 11 factorial and be done, but we have the repeats. So now we want to figure out what all the types are. Of those 11 letters, let's see how they break out. Well, we know there's one M, that's type 1. We know there's 4 I's, if we count them up. There's 4 S's, and then there's going to be 2 P's. And then as a check, we should count these up to make sure they add up to 11. 1 plus 4 is 5, plus 4 is 9, 2 is 11. So we have 1 of type M, 4 of type I, 4 of type S, 2 of type P. So the way to do this then is the number of permutations of the word Mississippi we're going to start on the numerator is going to be our 11 factorial. Again, what would we do if there were no repeats? And then we're just going to divide through by all the repeated types. So the first one's going to be divided by 1 factorial. Then we have the number of i's. There's 4 factorial arrangements of all the i's, 4 factorial arrangements of all the s's, 2 factorial arrangements of all the p's, and if we go ahead and do the math on that, you'd get 34,650 ways to rearrange the letters in the word Mississippi. Okay, so hopefully you've got the gist of this by now. So example 2 is just a different spin on it. In this case, instead of rearranging letters, we're going to rearrange numbers. So the same thing is how many different integers can be formed using all the digits of 253, 225. And again, these 2's are going to be indistinguishable, as are the 2 5s. So the first thing we've got to ask ourselves is, what's the total number? Well, there's 6 digits here. Now, what are our different factors? N1 is going to be 3, which is the number of 2's. N2 is going to be 2, which is the number of 5's. N3 is going to be 1, which is the number of 3's. Clearly the order that I do these in doesn't matter. That's just the way I counted them up. And to get the number of permutations, start off with 6 factorial as if there were no repeats, and then just cancel out the repeats. 3 factorial, 2 factorial, 1 factorial. Do the math on that, and you get 60 different ways you could write that, or write the 6 digits shown here as a different number. This last example is kind of a clever way to use this approach to solve a problem that in some ways isn't really related to rearranging letters. The problem here, just to give context, is I'm standing in the city here, and I'm standing at point X, and I want to walk to point Y. And in this particular problem, I'm only going to allow you to travel south or east. So south is down, and east is west. Sorry, east is this direction. So you're probably asking yourself, well, what does repetitions and permutations have to do with this problem at all? Well, the first thing to recognize is in a problem like this is, well, how many blocks do I actually have to walk to get from X to Y if I'm only allowed to go south and east? Well, it looks like it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I took a different path, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all these paths are actually 10 blocks long. And again, I can only go south, but when you think about it, how many souths, I'm sorry, I only go south and east. Well, if I do this, I have to go east, 6 east blocks in order to get here. If I don't go 6 blocks east, I'm never going to get to Y, and I have to go 4 blocks south. And so the way to think of this problem is it's really just a way of rewriting. Like if I actually wrote the letters of my path that I took, I'd be like east, south, south, east, 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 south, south, east, east. And that would be an example of a path I could take. There's going to be 10 blocks here, and there's going to be 6 E's and 4 souths. And so a way to solve this problem then is, well, I can just think of this as rearranging those 10 letters when there's 6 E's and 4 S's to get me all the different paths. And so the number of paths then, in this case, would be 10 factorial, number of ways to arrange all these blocks, but I know that there's 6 E's and 4 S's, so I'm just going to cancel out those repeats. And that's going to get me 210 different paths through this grid where I'm going 6 blocks east and 4 blocks south. Now the only reason this particular approach worked is because in this problem I forced myself only to be able to walk east and south. When I do that, that fixes the number of blocks at 10. So for this last part of the chapter 15.4, we're going to consider circular permutations. The standard permutation we've been working with has been referred to as a linear permutation. And so this part is going to talk about or help us deal with situations where we want to arrange people around a circle as opposed to just in a row. So let's think about seating 4 people around a table. We're going to call them A, B, C, and D. If we were going to seat them in a row instead of around a table, and I asked you how many ways could we seat them in a row, well, this would be just simply 4p4, or 4 factorial would be the number of ways A, B, C, and D could be seated in a row of 4. But now let's think about a table. Let's put one arrangement here. We're going to put A at the left head here, A, B, C, D, and just go around the table. A, B, C, D. Now the next arrangement I want to look at is, let's say we just move everybody one position around the table. So we have A at this seat, B, C, and D. And then we're going to do the same thing again. We're going to move everybody one spot around. A, B, C, and D. And then the last thing we're going to do is move them around one more position. A, B, C, and D. Now I want to think about what linear permutation would have resulted from this. So what I'm going to do is I'm just going to write the letters in order, starting with whatever's on the left here. So this would have been the linear permutation A, B, C, D. This one would have been D, A, B, C. This one would have been C, D, A, B. This one would have been B, C, D, A. So if these people were sitting in a row, these would have all been different permutations. But then if we go ahead and just put these arrangements at a table, we're going to consider them all the same in the following sense. Like, for example, if we look at person A, go ahead and highlight person A. If that person looks to her left, she's going to see B. She looks to her right, she's going to see D. Well, that same thing is going to happen at this arrangement. Look left, see B. Look right, see D. Same thing here, and same thing here. So when they're sitting around a table, we want to consider these 4 to be identical permutations. So then the question we're asking here is, well, how many circular permutations are possible when seating 4 people around a table? Well, to answer this question, if we were going to seat them in a row, again, it's just like the permutations with repetitions, we're going to start off with 4 factorial would be the number of possible starting ways before putting them in a circle. And then, as this diagram shows, we have to undo the fact that we're going to get some repeats when we put them around the table. And the way we're going to undo that with circular permutations is we're really just going to divide by 1 over 4. So for every, in this case, for every 4 like this, we're going to consider them one in the same here. So for this one, we could simplify this actually as 1/4 times 4 times 3 factorial, and just simplify it down to 3 factorial equals 6. So not surprisingly, if we want to generalize this, the number of circular permutations is going to be, of n objects, is going to be n factorial times 1 over n out in front, to undo, or to basically account for the fact that when we put them around a table, we lose some of these distinct permutations. So a pretty easy formula to remember. And that wraps up our video for chapter 15-4.